You are welcome to the GMAT's 41's Engineering Mathematics class. In this video lesson, I'll be teaching you Cayley-Hamilton's theorem. We are going to state this theorem and then use this question we have here on the board to verify the Cayley-Hamilton's theorem. In our previous class, I taught you how to determine the eigenvalues and the eigenvectors of a given matrix. And one thing very important that we learned there was that to determine the eigenvalues, of course, we need what we call the characteristic equation of a matrix. And so from there, we learned about the characteristic equation of a matrix, which we said it is that matrix minus the eigenvalue representation. Of course, we use lambda in that case, multiplied by the identity matrix. And the identity matrix must be the same in terms of its order. It must be the same as the order of the matrix you are dealing with. If you take the determinant of this matrix minus lambda times I, you are going to get 0. Of course, we were able to use that characteristic equation to obtain the eigenvalues. Interestingly, in Cayley-Hamilton's theorem, we also rely on this characteristic equation. So of course, I want to believe that this Cayley-Hamilton's theorem is going to be a simple one for us to understand. Is that okay? Having said this, I'd like us to state the Cayley-Hamilton's theorem, and then we go straight on to solve this question on the board. What does the theorem state? Cayley-Hamilton's theorem states that every square matrix satisfies its own characteristic equation. Every square matrix. Remember, in this case, we are dealing with what? Square matrix. So if I give you any square matrix, that square matrix will satisfy its own characteristic equation. And what do we mean by the fact that it's going to satisfy its own characteristic equation? It's simple. If you have the characteristic equation, say A minus lambda I, and you take the determinant of this A minus lambda I, you're going to get 0. Now that it satisfies the equation simply tells us that if you carry out this simplification, A minus lambda I, alright, its determinant, when you simplify it, the equation is going to balance. That's to say, the left side will give you 0 as well as the right side being equal to 0. You know what we mean by maybe balancing an equation. Like in linear equation, if somebody gives you x plus 3 equal to 5, you know x there will be equal to 2. And how do you know that the x is 2? If you substitute that 2 for x there, you have 2 plus 3 equal to 5. And 2 plus 3 is 5. So 5 on both sides, it balances. So the same with Cayley-Hamilton's theorem, relating it to the characteristic equation of a given matrix. If you simplify this determinant of A minus lambda I, it should give you 0. Please, let us go straight on to verify the Cayley-Hamilton's theorem, solving this question we have here on the board. Now we have this matrix. It is expected that we verify the Cayley-Hamilton's theorem for the matrix here on the board, 604 minus 213, 204. So what do we do? Straight on, we would go to the characteristic equation. That's the first thing we need to remind ourselves of. And of course, according to Cayley-Hamilton's theorem, it states that every square matrix will satisfy its own characteristic equation. And that is why we need that characteristic equation a lot. And of course, this is how simple the characteristic equation of a given matrix looks like. Okay? Simply the determinant of A minus lambda I equal to 0. Now, all we're going to do is to substitute into this characteristic equation, and then we simplify whatever we have there. Remember, this slash sign represents determinant of this whole term. So let us substitute and see. Our matrix A is 6. So we're going to have 6, 0, 4, minus 2, 1, 3, and then 2, 0, 4. This is the square matrix A. Of course, it's going to be negative lambda I. What is our I in this case? I is an identity matrix, a unit matrix, we know that. And the order of this matrix I must be the same order as the square matrix you are dealing with. This is a 3 by 3 square matrix. So the identity matrix will take the form 1, 0, 0, 0, 1, 0, 0, 0, 1. Good. when we take the determinant of this whole term, it's expected to be equal to 0. That's what Cayley-Hamilton talks about. And the 0 here simply means this is a 3 by 3 square matrix, you know. So the result we're going to get after simplifying this should balance, giving us a 0 matrix, a 3 by 3 0 matrix. So we want to verify that and see. If I simplify this term, okay, I am going to get a 0 matrix. Now this is what we're going to do. Let us simplify this term before we proceed to obtain the determinant. And of course, you know, this is very simple. This lambda is going to multiply each of the elements in this identity matrix, which means that this 1 is going to be lambda times 1, which is lambda, and then you have lambda times 0, which is 0, lambda times this 0, which is 0. Do same, use lambda to multiply this 0, you get 0. This will give us lambda, this is 0. Use lambda to multiply this, you get 0. This will be 0, and this will be lambda. Then what you get there, you subtract it from this matrix. Let's go straight on to do that, please. Okay, I've simplified this term. I've used this lambda to multiply each of the term of this unit matrix. So subtracting, by simplifying this term, we are going to get the determinant of this minus this. So let me subtract this term first and see. 6 minus lambda, we have this. Okay? And then the element in row 1, column 2, minus the element in row 1, column 2. That is 0 minus 0, get this. The next is 4 minus 0, and we'll get 4. Then coming over to the second row, minus 2 minus 0, we get minus 2. Then 1 minus lambda, we have this. 3 minus 0, we get 3. And then the third row, 2 minus 0, gives us 2. 0 minus 0, we have 0. Then 4 minus lambda gives us 4 minus lambda. I've simplified the term that we have here, a minus lambda r. This is what I got. It's expected that if I obtain the determinant of this term, and of course substitute the given matrix, it's going to give me 0. Alright, now we're going to proceed to obtain the determinant of this matrix now. And so I'll put plus, minus, and plus. I'll be fast in obtaining the determinant. You know how we do that? This is a 3 by 3 square matrix. So we pick this term, keep it constant, delete the column, delete the row, find the determinant of the 2 by 2 square matrix that will be left. Do the same for this 0, pick it as constant, delete its column, delete its row. You get this 2 by 2 square matrix, find its determinant. And then lastly, pick this plus 4 as constant, delete its column, delete its row. You get this 2 by 2 square matrix, find its determinant. And then you equate to 0. Let us see what this characteristic equation of this matrix is going to produce for us. We have this. So next we're going to pick this plus 4. But anyway, this minus 0 times, this time I did as a waste of time. When I pick this minus 0 as constant, deleted this column, deleted the row, this times this, minus this times this. It's a waste of time because whatever I get there times 0 will give us 0. Are you following, right? I just had to show it. It's not necessary. Take note. Because this term is 0. 0 times any term vanishes. It becomes 0. Okay, so picking this plus 4, delete the column and the row of this 4. So we get this is going to be equal to 0. I believe you understand what I did here. Just simply getting the determinant of this 3 by 3 square matrix. Now it is left for us to simplify this term to see what we are going to get. Already, like I said, this will become 0. So let's just cancel it off. We are left with this term and this term. And so this implies that 6 minus lambda times this term minus 0. This 0 goes off, we are left with these 3 terms. Then coming over to this, simplifying from the term in the bracket, this is minus 2 times 0, it goes off, so this term is 0 already. And then this is minus 2 times this term. We are multiplying it by plus 4 outside, plus 4 times minus 2 give us minus 8. So it's simply minus 8 times 1 minus lambda. And this is plus, so I have 1 minus lambda, so we get 0. Now at this point, we are going to expand this equation. Is that okay? These terms we have here, we're going to multiply this 3 bracket out. We're going to use this minus 8 to open up this bracket. Is that okay? Take your time to do that. Open up this bracket, open this with this minus 8 and simplify. If you do that, you're going to get this polynomial. Lambda cubed minus 11 squared lambda plus 26 lambda minus 16 equal to 0. This is the resulting polynomial. Alright, now according to Cayley-Hamilton's theorem, once we are able to get this equation, all we now need to do is to substitute the given matrix for the lambda that we have here, which means I'm going to evaluate P of A, where this P of A represents polynomial in terms of A. So this means that in place of this lambda, I'm going to put A. It's just like, in elementary mathematics where we deal with remainder theorem, okay? If you're given a polynomial, they say, okay, find P of 2. You go to that polynomial and then in place of the variable there, usually x as we use, you fix 2 for x and then simplify. So in this case, we are going to obtain P of A, where A is the given matrix. So according to Cayley-Hamilton's theorem, when we fix A into this equation and then we simplify, we're going to get a 0 matrix. Is that okay? So this means that in place of this lambda, we're going to have A raised to the power of 3 minus 11 times square of A, then plus 26A minus 16 equal to 0. Good. Now we're going to substitute for the matrix A now using the given matrix here, and then we'll resolve and see what this left-hand side is going to give to us. Of course, according to Cayley-Hamilton's theorem, we expect that it's going to give us 0. That is what we are trying to verify. Is that okay? So let us do the substitution and see, to fix in the value of A, this matrix, we fix it into this equation, and then obtain the value of A cubed, A squared, and simplify that. But to do that, this 16 is a constant. You cannot add or subtract a constant, okay, from a matrix. Therefore, this 16, which is a constant, has to be converted to a matrix. And to convert this 16 to matrix, we're going to multiply it by the identity matrix, a 3 by 3 square matrix, since the matrix we are dealing with here is a 3 by 3 square matrix. Just like we did here, multiplying this lambda is a constant. We have to multiply it by the identity matrix so that this subtraction will be possible. Once again, remember, you cannot add or subtract a constant from a matrix. So let us do the substitution, please, and then simplify to see what we get. Remember, we had A cubed minus 11 squared A plus 26A, and then minus 16 equal to 0. And then I told you that this 16 has to be converted towards a matrix. So I'm going to multiply this by the identity matrix I, and then equate it to 0. Doing the substitution, this is going to give us A cubed. A cubed simply means this matrix multiplied by itself 3 times. This is what we're talking about. This will be raised to the power of 3. In fact, let me write it out here. Power 3. And then we have minus 11 multiplied by this time to the power of 2 plus 26 multiplied by same matrix, and then we're going to have minus 16 multiplied by the identity matrix. Good. This is what we are solving. If we work around this, we are going to get 0. Okay? So let us work around this and say we are going to evaluate A cubed. We're going to evaluate A squared. And then we'll multiply this value of A squared by 11, multiply this matrix by 26, and then this identity matrix by 16. Follow this mathematical sign and then simplify. We're going to get 0 matrix. That's the idea of Cayley-Hamilton's theorem. So let us do that. One of the key ways to approach this is to obtain our A squared. So we're going to take that one after the other. A cubed is equal to A squared times A. And of course, to do that, it means we need to obtain our a squared. And what is our a squared? 604, okay, minus 2, 1, 3, then 204. We're going to multiply it by itself. 604, 213, 204. This is very important to us. This is the value of a squared. So whatever we get from here, we'll now multiply it by that same matrix. And of course, we know how to multiply our matrix already. It's going to be row 1 times column 1. As you're multiplying, you add the terms you're getting. Any answer you get will be in row 1 column 1 of the new matrix a squared you're trying to get from here. Next, row 1 column 2. Any answer you get will occupy row 1 column 2. Next, row 1 column 3. The answer you give will occupy row 1 column 3 of the new matrix you're trying to obtain. Then you move on to row 2 column 1, row 2 column 2, row 2 column 3, row 3 column 1, row 3 column 2, row 3 column 3. Any answer you get will occupy the respective row and column of the multiplication you did. Alright? So you work on that. If you do so, this is going to give you, let's find out what this a squared would be. Now that is a squared. It's going to give us, that's our a squared here. And then remember that we are multiplying it by this to get our a cube. Okay? So a cube will now be equal to 44040 minus 817 20 024 multiplied by 604 minus 213 204. You follow the same pattern of this multiplication. Are you following? Rows times column, okay? We are going to obtain the value of a cube to be equal to, so this is the value of a cube. Until we are done with a cube and a squared, we don't have problems with them anymore. All we need to do is to substitute and then simplify. So it implies that our a raised to the power 3 minus 11a squared plus 26a minus 16i is going to give us a cube 3, 4, 4, 0, 3, 3, 6. We have 36, 1 and minus 1, okay, 168, 0, 176. This is our a cube. Of course, we said we are going to do minus 11 times this 10. Minus 11 times a squared. And a squared we obtained it to be 44, 040, minus 817, 20, 024. Good. Now we'll move on to plus 26 times this term. That given matrix 604, minus 213, then 204, minus 16i. Once again, simplifying this, you should get a 0 matrix. Okay, so we are left with multiplying this term out and then carrying out this operation that we have here in the box to get 0. So let's do that and see. So we have this matrix here. Remember, this is our a cube. This is a raised to the power 2. This is a matrix A. And of course, this is our identity matrix. So what we're going to do here is to multiply this matrix, okay, each of the elements of this matrix A squared by 11. We'll maintain this sign outside. Are you following? We just use 11 to multiply. Don't use minus 11 to multiply. If you use minus 11 to multiply, automatically the sign that will be here will now become plus because the minus has gone in. I always advise just use the number to multiply. Maintain the negative, okay, so that minus will now become the operation you're carrying out with. Again, we're going to use 26 to multiply the elements of this matrix A. Then we'll use 16 to multiply the elements of this identity matrix. After which we simplify what we're going to get by normal addition and subtraction of matrices. And of course, according to Cayley-Hamilton's theorem, we expect that we're going to get 0 matrix after the whole simplification. So let us do that and see. Remember, I've told you we're going to use this 11 to multiply these terms here. Use 26 to multiply this element, 16 to multiply this element. This will produce this matrix for us. A cube will remain. And now, this 11 multiplying this term will produce 11 times 4, 4. That is 44. It's going to give us 484. You can work out the others. We get this. Then this takes us to 26 times this element of matrix A here. And we get plus. And then the next will be minus 16 times this identity matrix. Of course, minus 16 times the identity matrix, we're going to get this term. So this is expected to give us 0. Can we now simplify this term and see? Are you ready? Let's do that. It implies that 334 minus 484 plus 156. If you do that, it's going to give you 16. This element, row 1, column 1, minus row 1, column 1 of this, plus row 1, column 1 of this, you'll get plus 16. Then minus this 16 will give us 0. Okay? And then next, we have element in row 1, column 2, minus element in row 1, column 2 here. Okay? Plus element in row 1, column 2 here, you get 0, you know. And then minus element in row 1, column 2 there, you get 0. This is playing out now. We move on to the next one. Element in row 1, column 3, 336 minus 440 plus 104. If you do this term, 336 minus 440, if you work it out, of course, you are going to get a term that is minus 104 there. Are you following? You get minus 104. Then plus this 104 will give us 0. Then 0 minus 0 will give us 0. You move on to row 2 and do the same thing. 36 minus 18 minus 88. And then plus minus 52. If you do that, you get 0 minus this 0. That produces 0 for us again. And then you proceed in that way. Element in row 2, column 2 here, 1 minus 11 would give us minus 10. Minus 10 plus 26 would give us 16. That is plus 16. Then plus 16 minus 16 here will give us 0. You can work for the rest, okay? For minus 1, minus 77, and then plus 78 minus 0, you're going to get 0 again. Move on to row 3, okay? Row 3 and pick them corresponding element to corresponding element. If you do that, you still get 0, 0, 0. So do you see? That proves it. That proves our expression, okay, according to Cayley-Hamilton's theorem, that every square matrix satisfies its own characteristic equation. You see that at the end of everything you got 0 matrix, and this proves it. That is all about Cayley-Hamilton's theorem. So what did you learn from the whole thing, you know, that was done in solving this question? It's simple. Once the problem is given to you to verify Cayley-Hamilton's theorem, simply quickly record your characteristic equation, okay? Characteristic determinant equation A minus lambda I, that determinant equal to 0. Do your substitution using the matrix given to you, and the identity matrix whose order must be the same as the order of the square matrix you're dealing with. Obtain the determinant of that expression. Simplify and get a polynomial. Substitute the matrix for the variable you use in that polynomial, usually lambda, okay? Substitute the matrix into it. And then simplify whatever you get. As you do that, you will get a 0 matrix, and that verifies Cayley-Hamilton's theorem.